Welcome to our second screencast of the electrokinetics module. Now we will discuss the Butler Volmer equation, which is really a key equation for electrokinetics, and I'm sure you will use it quite often. In our previous screencast, we discussed how we deduce this equation, namely the current density is the exchange current density multiplied by this E power, which contains the alpha and the anodic transfer coefficient and the eta, the overpotential of the reaction. So you can see here the dependence on the potential with 0, 0, with meaning the point where we are at equilibrium potential. So we can make a similar line for the cathodic current density, the red line. The cathodic current density is negative because it's a reduction reaction. So basically that's the key difference. We have this minus here, and of course here we have the cathodic transfer coefficient. Now for simplicity, we assume here that both the anodic transfer coefficient and the cathodic transfer coefficient are the same. Now we can combine these lines into the gray line, because actually at any potential the cathode of the oxidation and the reduction reaction do occur. Only normally one of the reaction is dominant. So at high potentials you only get the oxidation reaction, and at low potentials you get the reduction reaction. Only at the equilibrium potential both reactions cancel each other out. But this equilibrium potential is a very interesting point, so we should not forget about it. Now together this gray line we can represent with the Butler Volmer equation, which is written down here, and it's just the combination of the blue one and the red one. So we see it here with the I0 in the equation, the alpha A and the alpha C. So this is the Butler Volmer equation, so really a key equation in electrokinetics. On the previous slide we wrote the current density as a function of the overpotential, but we can do it also in the other way around, as shown here. Here the eta is a function of the current density, and it's basically still the same equation. Well, a small difference is now that we use the 10 log instead of the natural logarithm. That's also why the 2.3 suddenly turns up in this equation. Now, the reason for using the 10 log I will explain later. This is for the anodic part and also for the cathodic reaction or the reduction reaction. This is the equation. The graph here shown here is still exactly the same because we haven't changed anything to this graph. It's only to show that you can also rewrite the equation. Now, why did I rewrite it that way? Because now I can move towards the tafel slope. And another step I make in that process is that I change my y-axis. Instead of just the current density, I now plot there the log of the current density and actually the absolute value to avoid any issues with having to deal with the log of a negative value. Now we see that we get a straight line, as we could expect based on the mathematics. And this line has a particular slope. And the slope of this line we call the tafel slope. Here you can see that for this process, the tafel slope is 2.3 RT alpha N F. The same we can do on the cathodic side, where we can also write down the tafel slope. Now it's of course helping that we took the log of the absolute current density, otherwise this would not work. But here again, the slope of this line is now 2.3 RT and divided by the cathodic transfer coefficient and NF. So we have these two lines. Obviously the total net current, that's still the gray line, is now a bit more complex. because in principle at the equilibrium potential the net current is zero, but that we cannot plot on a logarithmic x, so that is why we see this current here moving towards zero. And what you can already see here, and that is important to notice, is that this Tafel slope you can accurately determine at high overpotential. At low overpotential, it's a concept that doesn't really work, because then both the anodic and the cathodic reaction are occurring at significant rates. But at high overpotentials, you see the clear value of the Tafel slope. And this is very relevant in electrochemical experiments. So we will come back to that in our module on laboratory techniques. Now, a couple of things to remark on that. Normally we express Tafel slopes in millivolt per decade. And that's actually why we use this 10 log instead of the natural log. We could also have used the natural log, but somehow in the world of electrochemistry, people are used to using the 10 log. And if everybody does it, you can either try to fight it or you can just adapt. And that's, in this case, probably the best way forward. For basically what I've shown here, all applies to a simple one electron transfer process. And then you can actually, for an alpha of 0.5, which is a typical value as mentioned before, you can calculate that the Tafel slope is about 120 millivolts per decade at room temperature, because you can just fill in this equation, which is not very difficult. Now, for more complex reactions, that's no longer the case. Then Tafel slopes can also differ, and we will extensively discuss that in screencast 3.3. Now, to practice a bit with this, I would recommend you to carry out quiz questions 3.3 and 3.4. Now, what's the relevance of the overpotential? The overpotential is a large contributor to the cell potential. At least in most cases, it's a large contributor. There are a few exceptions, but typically it is an important contributor. And we can see it here in the equation. We have the cathodic overpotential and the anodic overpotential, because of course in an electrochemical cell you have both a cathode and an anode, and both of them have overpotentials. And yeah, as we discussed already before, the cell potential is just a very important key performance indicator. So if something influences the cell potential, it is relevant. Now, what is important to note here is that the overpotential has this current density dependence. So you cannot say for a certain process it has this and this overpotential. You should always say it has this and this overpotential at this current density. Now, for this, with this I would like to conclude this section on the Butler Volmer equation. In the next section we will discuss the more complex electron transfer processes and what that means for the Tafel slope and hence the overpotential. Thank you for your attention.